Hello students, in today's video we will discuss about angular momentum of a particle. Angular momentum of a particle about a point is defined as the moment of its linear momentum. Unit of angular momentum is kilogram meter square per second. It's a vector quantity. Just as the moment of force or torque is the rotational analog of force, the quantity angular momentum is the rotational analog of linear momentum. Now we will find out angular momentum of a particle. Let us imagine m is the particle situated at r distance away from the origin O in the xy plane. So this is the x-axis, this is y-axis. Let us imagine p is its linear momentum which is acting through an angle theta. So this angle also is theta. Now the line of action of momentum is this line and its perpendicular distance from the axis of rotation to the line of action of momentum is ON. So this is a 90-degree angle. Now we will find out the angular momentum L. Angular momentum L is momentum P into the perpendicular distance from the axis of rotation. So it is P into ON we can write. What is ON? We will find out what is ON is. So ON is, we can find ON from sine theta. Sine theta is equal to ON divided by R. So ON is equal to R sine theta we get. Therefore, L is PR sine theta, or even it can be RP sine theta also. So from the relation, the vector L is equal to, we can say R cross P. So where is vector L found? Vector L is found in a plane perpendicular to the plane containing R and P. So this is the direction of the vector L. The conditions under which L becomes 0 are like the conditions we learned in the previous video for torque when all it will become 0. Similar conditions are there for angular momentum to be 0. So it may be, so L minimum value is equal to 0. That can happen when R is equal to 0 or P itself is 0, that is its velocity is 0. P equal to 0 means P is mv. M cannot be 0. So in the product V has to be 0 so that P will be 0. So the particle is not moving, or if the particle is situated at the origin, or the other condition is theta is equal to 0 or 180 degree. 0 means P and R are parallel to each other. 180 means they are anti-parallel to each other. We will find out a relation between torque and angular momentum. The physical quantities torque and angular momentum have an important relation between them. The angular momentum, as we mentioned earlier, it is the rotational analog of the linear momentum, as well as torque is the rotational analog of force. So for deriving the relation between torque and angular momentum, what we have to do is we will find out the derivative of R cross P with respect to time. So this will give us, this has to be done in the UV method of differentiation because R and P both are variables here. So we'll do R cross dP by dt plus dr by dt cross P. This is how we should do the differential. It is the method like this: duv by dt is u into dv by dt plus v into du by dt. So this equation 1, what we have to do, actually what we have done is dl by dt because L is R cross P. So what we are getting is dl by dt is equal to R cross dp by dt. What is dp by dt? dp by dt, from the second law, we know that differential of momentum with respect to time is nothing but the external force applied. So R cross F plus dr by dt is the first derivative or differential of the position. So it will give us velocity cross P. P is mv. So we know that two identical vectors, velocity over here, when you find the cross product, its result will be equal to 0. So v cross v is equal to 0. So this term as a whole becomes 0. And what happens is, so this term became 0. That means the differential of L with respect to time is equal to just R cross F, which is nothing but the torque. So what we understood is torque is the time rate of change of angular momentum. In this question, show that the angular momentum about any point of a single particle moving with constant velocity remains constant throughout the motion. So the information given here in the question is the particle is moving with a constant velocity v. That is over here. The direction is shown in the figure. Then now the position of the particle is at P. Now the question is asking you if it was at about any point, need not be at this point, it may be here or here or here, whether the angular momentum will remain constant or not. So when we find the angular momentum, what we want to know is L is R cross P, or it is Rp sine theta. P is nothing but mv, so this can be written as mvr sine theta. Now mass is a constant for the particle. V is also constant. The question says V is constant. So if L has to be constant, what need to be constant is this value called R sine theta. Where is R sine theta found? Let us take this triangle OMP. It's a right triangle OMP. In that we will find out sine theta. Sine theta is OM divided by R. So OM is nothing but R sine theta we get. So we'll check whether this OM has any difference if P, the point P, changes to position P1, P2 or P3. So let us take these distances like this. Here all R is only changing. The value OM, which is R sine theta, is not changing, because the angle adjusts itself such that the product R sine theta will remain constant. So what is happening is here L is equal to mvr sine theta. In that equation we can say, already we know m is a constant, v is a constant according to your question. R sine theta, which is OM, is also a constant. It does not change. The perpendicular distance from this point what you selected O, from that to this line of action of velocity, the perpendicular distance is not changing. Since all these three values are constants, L is found to be a constant. So what we need to know is the different positions, at different positions of this particle, the R sine theta value will remain constant or not. That is what you have to check.